Thank you, Mr. Chairman, for your introduction. Today I'm here on behalf of the main author, so Silvia Meschini, to present this research work. Today research work is joint research work between the University of Turin and the University of Brescia. I'm an associate professor from the University of Brescia. And this research work is a sort of an output of the Data Sensing and Analysis Committee of EC3 conference. Let's start from the motivation of our research work. In the last year, basically, there is a sort of tsunami of data because, you know, in the construction and built environment sector, we have a lot of data. One of the problem we inside in the DSA committee we start to manage is the problem of how data are managed by different workflow in the construction and built environment sector. One of the problems is that we discover is that different sector, like for example, carbon assessment or climate risk management, are basically based on a completely different workflow data analysis. For example, carbon assessment is performed using BIM for estimating LSEA. Climate risk generally is based using GIS mapping and remote sensing information for and produces an output flow and heat maps. This parallel workflow causes a sort of a fragmentation of how data are processed. What is one of the consequences of this fragmentation of the data workflow? One of the problems is that, for example, buildings or infrastructure that are designed in order to optimize the carbon assessment maybe the design is optimized in order to reduce, for example, the usage of materials in order to improve the LCA and to reduce the carbon footprint. But this exposes the buildings or the infrastructure to future hazards, like, for example, flood and heat risk. On the contrary, if we design a building or an infrastructure focusing only on the risk, climate risk analysis, the problem is to increase probably the carbon footprint of our infrastructure. That's why we need something we call digital climate indicators that try to basically to reconnect these parallel workflow. In the literature, we start, of course, with analysis of the literature, and we identify that there are a lot of currently available indicators for carbon assessment, for climate risk, resilience management, and so on. But one of the problems is that generally each of these indicators focus exactly on their domain and completely forgot the rest of the other domains. One of the problem in the case of these indicators is that each of the domain, like for example the carbon assessment or resilience assessment, are performed completely separately. So that means that the data collected by this domain sometimes misses some information. One of the problems is that we cannot generally integrate them easily. So that's why we define the digital climate indicator. Basically, a digital climate indicator is a computable metric derived from integrated digital artifact, for example, like BIM, EFC, GIS, and so on, in order to support climate responsive and resilient decision. A digital climate indicator, from our point of view, is not an additional score or an additional index, but is a framework which target is to harmonize the source of the information in order to allow the computability, the interpretation, and the validation of the index. So the idea is to have a sort of common information base that we can use for take the right decision from the point of view of carbon assessment, climate risk, and resilience performance. The three pillars of our digital climate indicator. We focus in the climate risk, we focus on urban flooding and urban heat. We select these two as a reference hazard in our framework because basically these two hazards has the high impact in terms of threats for cities and infrastructure, are supported by mature geospatial data and machine learning ecosystem, and they are both strongly connected to carbon and resilience decisions. Our framework is composed by 3 layers: the data sourcing, alignment processing, and the indicator computation. As I mentioned before, in the case of digital climate indicator, the data sources is heterogeneous, like for example, static data coming from BIM, IoT sensor, remote sensing map, and so on. And so the most important part is the alignment at the processing layer, middle layer, which role is to harmonize the information, the heterogeneous information that can be used by different the different workflow. And the role of this alignment and processing layer is to enrich semantically the information coming from sensor, to spatially match the information and harmonize this information before the estimation of the indicator. One of the key word of our approach is the completeness. That means not the need to generate more data, but to make the existing data usable, aligned, and interpretable in order to be used for the different estimation of indicators. In particular, in the case of the carbon assessment, we are using as an input for the estimation of information, BIM quantities, information about materials, operational profiles, and so on. For flood and heat risk, we are using as an input of our in our system other maps, heat matrix, and exposure data. And for resilience performance, we are using function, threshold, recovery assumption, and so on. A few words regarding an example of how it can be applied in a real system. Basically, our approach, we start by using the information stored in a BIM EFC. We enrich with information. We align the hazard layer, and so basically in order to geo-reference assets, match raster to geometry, and define aggregation rule. Then we harmonize the scenario for the estimation of the different indexes. So basically we harmonize the scenarios and the time horizon, and then we can calculate the estimator, the indicator for carbon assessment, climate risk, and resilience using basically the same common data sources. So, and this approach make the possibility, make the indexes we obtain comparable because are based on the same data sources. To summarize, what we propose in our work today is a sort of conceptual framework, which targets is to define digital climate indicators, focusing on 3 domains: carbon performance, climate risk, resilience performance. What we are proposing is not basically a new indicators, but an integrated framework in order to harmonize the input data in order to make the indicator coming from the 3 different domains completely comparable. What we are working on now is the application of this approach to real data set. We are working on the validation of the computation of this indicator. And one of the most important activity we are working on is the testing of the sensitivity of this approach in case of incomplete or unreliable, inaccurate information, because the output of the workflow of the data analytics could be affected by incomplete information or inaccurate information. That's all from my side for today. Thank you for your attention.